Okay, I hope recording should start. And today we have two lectures again. So as you noticed, that I tried to organize the course in the way that both lectures each day are usually somehow related to each other. So and today our major topic is what is called approximate nearest neighbor search. Um, you remember that the last lecture, like last two lectures, we discussed very simple idea. So what if we not index text as text, but what if we try somehow convert it into a vector representation? Yeah, and we succeeded. So we did some different approaches, but we never discussed the way how to put these objects into index, how to search them faster. So we know that doing a matrix multiplication of term document matrix by a query vector, we have what? We have like ranking. We have the values of how good the document matches with the query. But if you have this vector of 1 million of values, you need to sort it. And it takes like n log n time, usually, if you remember algorithms course. So how can we do it faster? How can we obtain the ranking in a fast manner? We will discuss it today during the next two lectures, 3 hours. Good morning. Okay. So these are the refreshment questions about the last lecture. So first of all, who can say what's the difference between vector and metric space? Because we will utilize these terms today. So what are the major differences? Can a vector space be metric? Can a metric space be vector space? And can they be different concepts? Like cosine similarity, vector can be matched. Some glances of ideas, but not ideas. So very simple, guys. Vector space means the space of vectors. What does it mean? The word space means from the linear algebra course. Space means a set with some operations defined. So if you say the vector space, meaning that the objects which we are analyzing are vectors, space means that there are some operations, and when we speak about vector space, these are what? Addition of vectors and multiplying by a scalar. That's it. When we speak about metric space, we don't define what is an object of a space, but we say that there is a metric, and metric is very like common term. Metric is a distance. So what there is a distance between an object and an object, and if we can define all possible pairwise distances, then it's a metric space. Say, and of course there should be some property. There's a triangle inequality, distance cannot be negative, like some obvious things. And of course, if here we don't define any operations and here we don't define the objects, of course we can merge them and there can appear the vector metric space in which vectors have some metric operation, and these metrics, as you mentioned, can be cosine similarity, Euclidean distance, and any metric which allows us to be positive, preserve triangle inequality, and so on. Can you provide an example of metric non-vector space?
Distance between points.
But points are they vectors?
Editor distance between words.
Yeah, editor distance. So the objects are words. The distance, editor distance, when we change one word to make another word. So the number of changes, and of course the number of changes can be bigger than if we have the intermediate word. So one word changed to another and then to another. So the whole number of edits should not be bigger than sum of these two edits. Okay, wonderful. I usually provide the example of chessboard. So the cells themselves are denoted with letter and number. So these are not vectors. They are just some text representation. But there is a rule to compute the distance by some figure, by a knight, by a pawn. So you can move here, so or by a king. So king is the universal piece, so it can move anywhere, and you can always compute the distance by a king from one cell to another. But cells are not vectors; they are just letter and number. Okay, next question. How similar and how different are latent space analysis and word-to-vec model? So remember, I tried to show you how they are similar. Do you remember what was the similarity?
some vectors into
Some what?
vectors.
Vectors?
I think this is the comments.
So what transform the some set of words to vectors?
No, yeah. Well, actually, we discussed only this topic last lecture, how to transform words to vectors. Do you remember that LSA was actually what? We take a matrix and we decompose it into multiplication of two matrices. One is projecting the text into latent space, and another brings it back. And the important thing was that the dimensionality, this one and this one, is pretty small. Okay, so that's why we love it, because we find a low rank approximation of a big matrix with two relatively small matrices. And we still can restore these metrics practically, like in a good manner. What about word2vec? Word2vec is a simple neural network, and it is like this. So here we have one hot encoding of, for example, context, then the hidden layer of the small dimensionality, and again the output layer, which is one hot encoding of the word, for example. And what is beautiful about neural networks, that each layer is actually what? A matrix multiplication plus nonlinearity. Okay, so actually the idea of word2vec is very similar to LSA, but the only difference is that what? We, instead of multiplying by a matrix, we add one more step. We add nonlinearity after. That's it, the only difference. So actually, it's like natural continuation. So what if our transformation is nonlinear? If it's nonlinear, then we can do even better. And that's why word2vec was that successful. Okay, and who remember what is DSSM and what were the differences between two implementations? So what is DSSM? What was the idea behind creation of this model, which was not present in word2vec? Maybe online. So what was the purpose of word2vec? To get encoding of word. No, that was the outcome, but the task was to solve some machine learning problem. What was the problem? Yeah, actually, syntactic and semantic similarities. Great. So there was the task. We have the data set, and we want, using this model, predict syntactic and semantic similarities of words. There were two data sets for this, and the metrics that provided in the paper, they are all related to these tasks. So actually, the paper is not about embedding into vector space. The paper is about predicting similarities. And when we speak about DSSM, it was created by Microsoft for the purpose of search, for Bing. Do you know this search engine? Is it still alive? Okay. And the purpose was to do what? To find the best match between a query and the document. Yeah. So, and that's why they predicted cosine similarity of a query in the document. That's why the network was designed in a different way. So here's a queue, here is a doc, and here are some deep layers here, and only here there appears prediction of cosine similarity. So it's like two-headed network. So one representation for queries, one representation for document. They are not exactly giving us the same space, the two spaces for queries and for documents, because they are of different length, of different nature. You expect more typos here and less typos here, and so on. So slightly different architecture. And this was the very interesting idea. So if we're here for information retrieval course, maybe we should search information retrieval problems. And Microsoft did an approach. It was the first approach. That's why this idea that was very had a very good adaptation in Yandex, because it's actually also doing search, and they did a lot of things. So first they added vocabulary, they extended the vocabulary of the network. Instead of just word trigrams, letter trigrams, they added most popular words, most popular bigrams. They slightly changed the architecture of layers, and most probably important thing was that they observed that click-through, so clicking on the document given query and the result, is not a good target. So what they said, that if you have good query and you have 10 relevant documents and you click on this one, does it mean that others are irrelevant? No, just because like this one attracted your attention, and when you do create a data set, you mark this as 0 and this is 1, and that's wrong. So not wrong, but this is a very bad way to train the model. Maybe you should do something different. And also, what about clickbait? Do you remember clickbait is something which attracts your attention, not being actually relevant. So usually it's porn and kitties, like two different topics which are attract attention. So wow, you didn't expect to see it here. You click and then you understand, oh, I was searching for like, the page about, Sandor Pushkin, and this is porn. I don't want this. And that's why the dwell time, the time you spend on the page was the better target, not just a click, but also the understanding that there is actually something interesting on the page. Okay. I hope these ideas are now settled in your mind, and let's move to agenda of today's first lecture. So we will start with the problem of, actually I think that the sequence will be, the sequence will be exactly the same. What is ANNS and not ANNS small? So like in the world of information retrieval, these letters mean slightly different thing. We will speak about how to achieve this with clustering and with extension of inverted index data structure. What is proximity graph and how to utilize proximity graph for information retrieval? And can we do something good with search trees? Are there search trees which are helpful in this case? So this is the agenda for today. Let's move slowly through the topics. Before we start discussing all these data structures, I want you to, like from your previous experience, bring back to the actual today's memory some concepts about about complexity. Do you remember the term complexity from the first or second year of your education? Algorithm complexity, time complexity, memory complexity. What was all this about? How many operations if we use a model, or time if we convert operations to time we spend doing something. Yeah, so some method, some algorithm, whatever. Great. And you remember how we discussed what was the inverted index. This is the usually hash table or some tree map where there are posting lists. So there are some collections of documents which contain this term, the word or term. Great. What do you think? What can go wrong here with the growth of data set? Imagine we started building inverted index when we had only 1 million of documents. And then our company became very big, and now we have 1 billion of documents. What will change in the data structure?
So I think the problem here is that when you go in big O notation, we have our complexity of algorithms like cubic or something.
In big O notation, we have cubic complexity of algorithm. Why cubic?
Like you have documents,
Mm-hmm.
and each word in document it needs to search in, like you need to for index, it has a less of documents.
Mm-hmm.
We have a lot of documents. While we need to search for these documents, we go into this index, and searching the documents in this last may take a lot of time.
Like obviously, if I say that there's something wrong in terms of complexity, yeah, it takes a lot of time. Like very simple observation. The vocabulary of our language is growing not that fastly. And if you have very frequent words, the frequency of them in language model, it doesn't change with time significantly. If they have the word cat, it will remain, for example, in 7% of all the texts and 7% of all the queries, okay? And that means what? It means that in your inverted index, there will be 7% of all documents of the whole data set attributed to the word cat. Okay, 7% for 1 million means 70,000. For 1 billion, 70 million. Okay, the list will grow 1,000 times. And also there will be 7% of queries with the word cat. Okay, so it means people will ask for cats, and if your service is growing, then even more requests will come to your service. And here's the question: if you do a complex query, a lot of terms, then you do what? You do intersection. Okay, and previously you would do an intersection of 70,000 of objects with, let's say, 10,000 of objects. Next time, when we have 1,000 more, like 1,000 times more documents, we will do intersection of 70 million with 10 million of objects. And intersection is not for free. Okay, it's usually a linear operation. That means that it is not scaling that good. Okay, so it means that inverted index was very good in some scale when we could grow and without observing real change. But unfortunately, the lexicon of our language is not changing that fastly. The words are not splitting, so the number of keys is not growing that fastly. That's why the documents should fall into the same buckets, and then we will work with very big buckets. So we need to find something which will create other buckets for us, and we will think about inverted index in a more generalized manner today. And also I want you to remember like these terms, so we will speak about them. What is the difference between these three notations? O of n, OA of n, EE of n.
A means asymptotically.
Actually, O is asymptotically. It's an asymptotic definition for O. OA means O. No. Only of. What's O of n? Lower bound is omega. It's like this. Yeah. So O of n is when you have some estimation of time for a function, and it will never exceed this limit. So if your function is growing as n, so all your implementations will grow as n or lower. So it means that for almost any function, I could just state it will be O of E of n. So almost any function in the world is at least exponential. Of course, there are functions which are even worse, but usually we think about such functions as about bad functions. Exponential time is when you double the time by adding a single element to a list, for example. That's a very bad behavior. OA of n, I usually mix this word with some other words. Let me remember how it's called in Russian, and maybe I'll translate. So I'm ashamed. Let me remember. Strange that you don't remember. Wow. So just my brain stopped working. Maybe you will help me. No, it's still O notation. It's about first year course. It's about when we estimate the complexity of hash table. You say that it's constant time, yeah, but it actually doesn't. Yeah.
In average.
An average. It's not.
That's what I mean.
It's not an average. It's aggregate. When you aggregate. Are there any words in English for aggregate? Joey?
Aggregate. Aggregate.
Aggregate. Okay. Other.
Isn't it amortized, I think?
Amortized. Wow. Thank you. Thank you. Amortized. Yeah. Definitely. So
it's a type of average, but it's not not like just taking the mean.
Yeah, so that's exactly. So it's not about averaging, it's about summing up. Yeah.
It is an average, but it's not a mean.
Yeah.
We go technical.
Okay. Amortized mean that we compute the computation time for a sequence of actions. And one particular action can take a lot of time. But we guarantee that after doing 1,000 of such actions, we still, like in total, do it fastly.
Amortized comes out of, if you were, say, like putting your rent, and you said, here's my rent over the course of the year, and you said, every month you will pay me this much, then you're amortizing the yearly rent over every month it costs you this much.
Thank you.
Accounting term.
Thank you, Joey, for comment.
No problem.
Yeah, and the idea of amortized complexity is that this is the way to show that even hash table is, for a particular operation, cannot perform constantly, but still in amortized way, it performs constantly because of the property that some hash functions will collide and some will not. And if you have enough space in our table, these collisions will, in average, grow our time by like a fraction factor. So it will be 1 plus alpha, where alpha is load factor. And if we just can influence load factor, then we're great. So if we allocate enough memory for a hash table, we can guarantee that alpha is be like less than 1. So it's like constant for us. Thank you. So sorry for this, like, strange situation. And also, there are some data structures, maybe, I don't know what you did take this in your algorithms course or not. Some data structures has the probabilistic nature. Maybe you remember I mentioned Bloom's filter. Maybe you will remember any other probabilistic data structures which are constructed in a probabilistic way. For example, skip list. So maybe those who used like competitive programming, they know about such data structures, which are not guaranteeing you anything. But we know that in average, the expected time is of this property. And for example, skip list is a data structure which is solving exactly the same problem as the search tree. But search tree gives you what? Gives you, for example, if you speak about AVL or red and black tree, gives you logarithm O of n time. And skip list can only say that in average, it will be logarithm. So the expected time is logarithmic. These two concepts are pretty similar because they don't guarantee the time for a single operation, but they actually can give you an estimation for how much money will you spend for a data center. Okay, so this one gives a strict guarantee. This one gives a probabilistic guarantee that for longer run, you will have this amount of money spent on this action. Okay, so let's go for more practical things. Approximate nearest neighbor search, ANNS. So in information retrieval, this term doesn't mean neural networks. It's about approximate nearest neighbor search. What's the idea? When you search for something exact, the obvious idea is the following. So if you want to be exact in matching an element with requirements, with a high chance you will do what? You will need to examine each element, except like maybe you are doing some indexing operations. But if you don't want to be 100% sure in the result, if it's enough for you to be almost sure in that the documents you retrieved are actual nearest neighbors, so you can go with approximate nearest neighbor. So it means that you are okay with 95% coverage. You're okay with this accuracy, with this precision, and so on. So, and of course, to even enlarge the share of relevant documents of those which are actual nearest neighbors, you can do some technique which will look like this. So you pre-select more. Taking more, you can guarantee that even more documents will fall into your consideration. And after this, you will select real neighbors out of this. So from this pre-selected set, pre-ranking set, this k multiplied by s. So you want for k nearest neighbors, you take c multiplier. So for example, 5. You want 10 elements, you select 50. And out of 50, you select 10 real nearest neighbors out of this 50. So you recheck. Yeah. So you first select somehow, and then you clarify the metric. So you define which are actual neighbors, and then you re-rank them if you have any re-ranking procedure. Which methods do we have for approximate nearest neighbor search? So if you dig through the literature, you will find like mostly 4 approaches. One is locality sensitive hashing, and actually I didn't see practical implementations in search engines for this. So they are practical, but I never saw like it in my life. So I worked with trees, I worked with graphs, but for LSH, I unfortunately didn't see any practical implementations. So if you can provide me an example of good system which works using LSH, I will be very pleased, and we can include this into the course later. What we will discuss in this lecture is search trees. Oh, sorry, in the next lecture, search trees and different supporting data structures like search trees. Idea related to vectors and clustering, hierarchical clustering and inverted index, and proximity graphs, which are the topic of this particular lecture. Okay, these are 4 approaches. Like when I saw papers in this topic, usually these 4 ideas are considered. So let's start with the idea with clustering. So you remember that we spent 3 hours last time on representing objects as vectors, and we can assume that we also know not only about the texts, but also about the videos, images, and so on. So not only texts can be converted to vectors, just believe me, you can do this for images, you can do it for any type of media, and we will consider it at the next lectures how to do this. So we know that there is a vector representation, and how can we use clustering in obtaining a good speed of search, and how to utilize this in inverted index. So first of all, do you remember what is clustering? Who remember? What is clustering?
Uniting elements by the closest elements.
Matching closest elements. So grouping them by some property. Okay. And actually, if you remember the machine learning course, maybe you saw this picture multiple times. It's scikit-learn documentation. And it shows that clustering is a very like poorly defined term. So clustering means we aggregate elements somehow, and this is aggregate and this is somehow are the subject of discussion. So for example, if we take one of the most often studied algorithm, k-means, yeah, this one, you will see that actually k-means is not about clustering the data. It's not about searching for good sets of similar documents. K-means is doing what is called, did you hear about Voronoi diagram? Did I mention it? So Voronoi diagram. So you want to create a kind of like a very good separation of a space. Yeah. So in the way that any cell in this diagram is very compact. So it tries to be as close to the ideal Voronoi diagram will be what? It will be a bee's hive. Yeah, so all these hexagons. So if everything is distributed uniformly, you will have these perfect blocks. Each of them is trying to become a circle. Yeah, in the multidimensional space, they will all try to become spheres. Okay, and the idea of clustering in k-means is that you take some elements as centroids, and you want to build like the friend zone of these centroids and say that these are my friends. And others will say these are my friends. Okay, there will be leaders and their friends. And if the data is distributed uniformly, they will just break in some cells with, as you see here, with like very straight borders. Like, here are my friends, here are not my friends. And this is very good when you want to split the data more or less in a similar blocks without actually considering their the meaning. So you take some data and I want to just partition it into some parts, and this is what is very useful for us. But if you like think about clustering in terms of human understanding, is it a good clustering or is it a good cluster? No, like we see that here is a cluster and here is a cluster, but k-means doesn't care about this, because the idea of closeness and aggregation is of the different kind. So they think in terms of metric, not in terms of connectivity. And on the other hand, if you speak about agglomerative clustering, dbScan, and so on, you will see that these algorithms are very good in defining connected clusters like this. So circles will stay circles, moons will stay moons, but this one will become just a single cluster. Okay, they just connect everything. And if you want to break the load on a system, if you want to use clusters to distribute the load on some parts, this one will be very bad friend for you. It will load one server and put empty data on others. So clustering can be different. They have different mathematical implementations, but the idea is that there are methods which try to split the space, and there are methods which try to split the data. And agglomerative clustering, dbScan optics, they will try to split the data. And they don't care about how big and how small are the clusters. K-means will be caring about the size of the clusters, about the neighborhood size. And that can be useful if you assume that your data is uniformly distributed. Okay, this is the few ideas why they differ. Because they use different linkage criteria. So, for example, if you speak about dbScan, if you consider this in a machine learning course, dbScan is the algorithm which is doing the following. So it starts from one node and tries to attract other nodes to the community if they are close enough. So if there is a support, there are friends who are friends of you and friends of this friend, and you say, oh, we know you, we will take you to our cluster. And if your cluster is pretty big, it will grow until it finishes all possible attributions. So they think about smallest distance. So you link a single item to a cluster, not caring about everything else. So if this one is good, we take it. If we think about the opposite case, the average distance and centroid-based approaches, they are about thinking about community. So we have a few communities and we want to see this particular guy. For this guy, is it better to be the part of this community or this community? Okay, so we look in general, we look either at centroid of this cluster, or we average the distances between this item and all items in the cluster. So that means that in this case, we just think about the, how to say it, it's like communism. So the good for everyone. So this is good for you, for one particular person. Will you take it to the community? This is for, are all the communities living with a good life? And some other methods in between. So for example, maximum distance means that you want to build the cluster in the way that you minimize the maximum distance among all the items here. And minimum energy is not about the distances. It's about, again, so if maximum distance is a well-defined term, here we speak about some energy. Energy means, for example, the variance. So there's a difference between variance and maximum distance. So maximum distance can be very big, but if there is a single element, it doesn't actually strongly influences the variances. So if you have a big cluster, one outlier will not strongly influence the variance. So these are similar concepts. So you actually think about the radius of your cluster. Is it big or is it small? But you speak in different mathematical terms, in terms of maximum and in terms of energy variance. Great. So you understand that these criteria about how to attach an element to a cluster can definitely influence the form of the cluster and the way how you distribute the data. Sorry. Yeah. So why can we cluster? So why it's useful to use clustering for indexing? Imagine that we have an assumption of uniform distribution of the data. So all our vectors representing the documents are uniformly distributed in some big space. And we have pretty big number of documents to think about them as about liquid, not about single elements, but like some liquid. Of course, if you have a flat list and you want to find best nearest neighbors, you will run through all the documents, compare them with dot product, and you will select those which are the closest. And of course, you know the algorithm which can give you like some order statistics, like case order statistics in linear time. Okay, let's say that we know the method, for example, k-means, which can split our clusters into a similar size. Okay, so you have similar size of clusters. Similar means the number of elements in each cluster will be more or less the same for all the clusters. And we take square root of n of such clusters, and obviously in average there will be square root of n elements in each cluster. Okay, you understand? So it will be like a two-layer tree. So we have some representatives for such clusters like centroids, and then each centroid is attributed with square root of n neighbors. What does it mean? So we first take these representatives, centroids of the clusters, and search for the closest one for our query among them. So it will be square root of n operations. Okay, so square root of n centroids. And then we found the centroid which is the closest. Then we jump into the cluster attributed to this centroid, and we do square root of n searches here. Okay, what's good here? The good is that we have two square root of n operations of comparisons instead of n. 2 square root of n is definitely better. Okay, what's bad here? Who can say?
If the query is on the bound.
Yeah, if the query is on the bound, we cannot guarantee that actual nearest neighbors will be in our result. So if we have in two-dimensional case these clusters, for example, and if our query is lying here, so we expect to have neighbors being here, and we will be able to obtain these guys because we use this cluster, but we never see these. Okay, so there's always something that you sacrifice. Here you sacrifice the neighbors, some neighbors, but like you pay for significant improvement in speed. Of course, if you do 2 layers, you can sacrifice even more neighbors. But if you can, you can come up with 3 square root of like root of third power of n. So and even more. So you create more layers, more partitionings, clusters of clusters of clusters. You can do even better, but you should stop at some time, because then you will be not able to take any neighbors. Okay, so we understand that clustering can be helpful. So we know what we pay, we know what we obtain in a good manner here. These are the techniques, the one which I observed like in practice in 2017 in Yandex, doing one of these 2 approaches. First, agglomerative clustering or divisible clustering. So agglomerative means what? You have elements, you glue them in clusters if they're close, and you grow them into this tree, and in the end you have a one big cluster, and you know this hierarchy, you can use it for search. Divisible, again, you take the cluster, you run k-means on this cluster, like you have all documents, you run k-means, you obtain some clusters of similar size, and then if you want, you can split them even further. All these approaches are acceptable. In my case, my colleague used divisible clustering. So it took him a few hours to split a couple of millions of documents, but he could guarantee a pretty good speed of search. He used this for if you ever saw in search, when you search for something in pictures, there is sometimes oh, maybe I can show it an example. Oh, you don't see it, yeah? So let me show some example, like for example, how we call it, refrigerator. I want the picture of refrigerator. Yeah, and if I search for picture, yeah, so today you see it like this. So it's mostly what? It's mostly shops. But if we, at one moment, previously it was not like this. So in search, for example, in Google, so you see it's all markets. No picture of refrigerator. Yeah, please stop. Yeah, and yeah. So the task was that given a picture of refrigerator, you should also suggest commercials, like some advertisement, and among these, yeah, you will see some markets like that. So some market which suggests you to buy a refrigerator. So, and he was building an index for such commercials, for such advertisement, and to suggest it in the picture search. That was the idea. But let me.
It's working. It's taken over everything now.
Yeah, the things are changing fastly, and you see that commercial is now first and pictures then. And previously it was pictures and then commercials. You see that they're aggressive and they want your money. Maybe Google have some problems. I don't know. Okay. So can we do even better? Can we use clusters for even faster search? So here's the Voronoi diagram example. Yes, if we combine the idea of clustering with an idea of inverted index. So as I mentioned, the problem of inverted index was what? The vocabulary is not growing. It means that the distribution of words is not influenced strongly by time, and you will stuck to these representations. You cannot change the word cat. So you cannot split it into two words which are like one will derive a half of a cat and the other will derive the half of a cat. If we move to vector space, if we can represent words with vectors, we have very good ability to group the words or texts in the like sets of any size. We want them bigger, no problem. We want them smaller, no problem. Okay, and instead of building the inverted index on words, let's do it on the clusters of vectors. It's maybe slightly confusing, but you remember what's the idea of inverted index? It's a hash table, meaning that this is the table of discrete objects. The word is discrete. We can compute a hash for this, and we then attribute some text here. Instead of this, let's create the set of vectors which will represent some conceptual term. Actually, we don't even know the meaning, but they are similar concepts. Cats, I don't know, leopards, lions, and so on will fall into this cluster. Okay, some cat meaning things. And then we will try to find a discrete representation for this, because this is the vector, and actually a set of vectors. Vectors are not discrete, they're continuous. And to do this, we can do some compression. There are two techniques of compression. There are vector compression and product quantization. So for vector compression, how can we obtain for a vector, for example, a centroid of a cluster, a discrete representation? The technique, which is produced by researchers and is implemented in FAIS library, Facebook AI Similarity Search, is very obvious. So let's, I can try to draw it. I'm not sure I'm good at drawing such things. So let's imagine that our vector of, let's say, of 128 dimensions. Okay. Then we will take a bunch of dimensions and consider them as a single feature. So we have these long vector, we will split this into bunches of blocks of features. Let's say by, I don't know, by 16. So it means that it will be 8 such blocks. 1, 2, 3, 4, 5, 6, 7, 8. So 128 at all, 16 dimensions, without any considering any meaning or everything. Just take these dimensions, okay? And then on these vectors, do clustering. So clustering. And having this clustering, you can define how many clusters would you like. For example, you want to encode these 16 dimensions of floating point values, means that 4 by 16, 64 bytes. You want to encode them with a single byte. So you do 16 times compression. How can you do this? I say, I want 256 clusters. Okay? And then we just give a number to each of them. Okay, so instead of using the actual value of the vector, I will assign the number to a cluster of some vectors which are close and give the discrete number to them. And having this, I will spend 1 byte per label here. Okay? Pretty simple technique. And then I can do product quantization. What does mean, product quantization? Instead of computing product for each vector, I represent in a compressed form the centroids, and I represent in a compressed form my query. So I just converted from this long version to a version of 8 bytes. And I just remember the table of multiplications, pairwise multiplication. So how it, or I pre-compute. So what will be if here I have 3 and 17, for example, the cluster 3 in query and cluster 17 in the cluster, so small cluster. And then I just remember the number and I take the lookup table and I extract this distance from here. And then I sum up these distances for all these pairs and I obtain the whole distance between query and the cluster. So my computation becomes 8 by lookup operation. Instead of doing dot product of 128 values, I do very fast computation in discrete form. So maybe to make it slightly clearer in your mind, let's think about this operation as about taking these values. So let's say, and trying to do quantization for each of the dimensions. So maybe I need a blank list. I don't know to draw. Can I create the new slide, empty one here? Control M and present. Is it possible? Yeah, great. So I can draw then even bigger graph. So I have the data like this. So for example, this and this. Then I remember the technique. I split the dimensions into groups. So here I have only 2 dimensions. So I'll take the group of first dimension and the group of second dimension. Okay. And what I do, I use the first dimension to cluster the data. And I say, I want to encode the values by the first dimension by 4 bits. Or even 2 bits. 2 bits will be enough for me. 2 bits means what? 4 different values. So I want 4 clusters by this axis. So I have all the data projected to this axis, and I then cluster the data into 4 clusters with k-means. For me, it will look like this. So I will have this cluster, this cluster, this cluster, and this cluster. So 4 clusters of k-means. And I will give them 1, 2, 3, 4. And I will repeat the same operation for another axis. So here are the values of y. And I will have these 4 clusters. So I will use only 4 bits in total to encode these vectors. Okay, and what will it mean for me if I then will try to restore the values? So I represent each cluster by a centroid, meaning that for any point, the responsible value for the coordinates will be here, 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 here. So I can draw it like this. And do it like this, okay? What does it mean? That all points which are attributed to, let's say, 2 and 2, so 2 and 2, these rectangles, so they will be here, and all the points will be approximated by this centroid. Okay, everything which is in this rectangle will be represented by this value. So when you understand that this is a pretty good approximation. Okay, so the idea of quantization is to find such an approximation which will not significantly move these points. So everything which falls into this rectangle will be moving towards the centroid. And this will happen for any such place. Okay, and the general idea of this method is to keep the product between the query quantized and the document quantized very similar to original value. So previously it was, let me use some color which I didn't use before. Previously it was multiplication of this vector, for example, by this vector. And now this is multiplication of this vector by this vector. So they changed not that much, okay? But you saved a lot of memory to represent. Instead of 128 floating point values, which is pretty big number. It's half of kilobyte of memory for each vector. You use 16 or 8 times less memory, and your computation becomes quantized. So you can do it in discrete form. So you just can remember lookup tables and do it in a constant time. So that's a significant improvement in real computations, not in the asymptotics, in real computations. I understand that maybe my explanation is not that perfect. So if you have anything you didn't understand, especially on the drawing, you can ask.
So we just made a clustering and encode each cluster by its coordinate, something like that.
The technique, let me go back to the slide. I hope it's still here. Yeah. So first, we split the dimensions into some blocks. Okay. We say that our vector will be represented not by 128 different values. It will be represented by 8 features. Okay. And each feature will be derived from 16 dimensions. Okay. And then we use clustering for calculating these features. But of course, these features will be discrete, and they are not actually somehow correlating with the values of vectors. And we need to do what? We need to each of these discrete values to attribute multiplication operation. So if previously you were multiplying, let's say 0, 0, 3 by some other vector, 4, 7. Now you multiply 1 by 3, and it should give you pretty the same result. Okay, so you redefine multiplication operation. You need some lookup table for this, but this table will be small enough, so it will be byte by byte. So it's 65,000 values, for example, and you just memorize all possible pairs, and you're done. So you're perfect. Yes, this product will be less accurate, but it will be significantly faster. And now you have this perfect thing. So you have these clusters. You know that they cover the whole space. And now you can use these discrete representations, like just a string of bytes, 8 bytes to represent any vector. And you can look up any query in this space. You go there, and you find the closest one, and then you search in this cluster as I explained the procedure. And you can vary the size of the cluster of the whole space to be small enough to be fastly searched inside. Woo, I hope at least a glance of idea. So just very simple observation that instead of using words, now we use clusters of vectors. We discretize them. We find the discrete representations for them to build an inverted index. And in this situation, we can balance the size of the cluster with the growth of the data set. The bigger data set, we can just adjust the cluster to be now smaller and now smaller with respect to the whole data set. Okay, so the number of words can grow, unlikely in the inverted index, which is built on words. Okay, do we have enough time? Yeah, great. So this lecture is not that big, so this method is for you. Next is what I love most. So this is my area of research. If you want to know even more about proximity graphs, you can come to 463, and I will say you a lot of things about proximity graphs. So let's start with the cheat sheet about the graphs themselves. So what is the graph? Just to warm you up. What's the graph, guys? Who knows? Vertices and edges. So graph is a mathematical object which is represented by a pair of vertices, so some set of objects, and edges. So it's a set of pairs of vertices. Yeah. So mathematically, strictly, it's like G equals V and E, where V is the space and E is some kind of relations in this space. So sometimes they exist, sometimes they don't. Okay. Graphs are used to model lots and lots of things: roads, electrical circuits, society, a lot of things. When we can define anything as a relation. So if you can define something as a relation, like I know you, you know me, or like there is a current going from one point to another, this is a relation, and graphs are perfect in this case. So they were invented by Leonard Euler. The term came much later. So he proposed the first theories in the middle 18th century. The term appeared in the late 19th century, so the term graph itself. But the theory evolved, and now we have a lot of different types of graphs. They can, first of all, can be weighted, directed, finite, infinite. They can be probabilistic. They can be like a lot of different types of graphs. So they slightly different here. So this can be a finite set or infinite set. This can be an edge which exists or an edge which probably exists, and so on. So there are multiple ways of constructing different types of graphs, and there are some concepts which cover all of them. So first of all, the term path is what? Is a sequence of edges. So if you want to go from A to H, there should be such a sequence, which you can, without skipping any edges, skipping any nodes, you can like proceed with going from one edge to another with some intermediate nodes, and you get here. And the length of the path is the number of such edges. So the path between A and F is 1. The path between A and H, here, if we define the path as A, F, C, D, E, B, H, is 1, 2, 3, 4, 5, 6. Okay. But of course, there's a shorter path. Yeah. So we can do like this, and we will end up faster. So simple path doesn't mean the shortest path. Simple path means that there are no repetitions. The shortest path means there are definitely no paths shorter than this one. Okay, one more term is degree. Degree is the number of friends. So if you have some connections, the number of your friends is a degree. So for F, it's 3. Okay, for G, it's 1. And also the graph diameter, the term which we'll use, is the longest, shortest path. So what does it mean, longest, shortest path? So among all shortest paths between all pairs of nodes here, we can look for such which will be the longest one. So I think that the longest one here will be, for example, from, I don't know, from H to A, or from H to G. So it's It's 1, 2, 3, 4. There's no chance I can take the longer path from here. So all others are shorter. So the longest among all the shortest paths is a graph diameter. And this is a very important property for the next explanation. Okay. The other type of, one of the type of the graphs is a random graph. Random doesn't mean that it either exists or not. Random means that the graph is created by some random process. There are a few models of how this random process is included in the building procedure. We don't cover it here. If you want to read the Wikipedia article, you can do. It means that this is the graph, so in this model, with a fixed number of vertices, and the edges will be created in some random manner. So when the graph appears, it looks like a random figure. Of course, you can have a slider which can influence how many edges would you like. If there is some probability value, which can, if you move it to the 0, there will be almost no edges in the graph. Yeah, so probability of creation of an edge is small, no edges. Probability of creation of an edge is big, almost complete graph. Okay, so there is some ways of influencing the creation of the graph. Previously, as we didn't know anything about our society, so some people know, some people don't know anyone. Previously, like in the early 20th century, these kind of graphs were considered as the model of social network. So we know each other, our friendship is defined as the relation, as an edge. People are vertices, and we say that the model of our society is a random graph. We somehow created the graph. We can sample some people and say this is the average degree. So let's build the random graph with the similar properties, and so on. So what's good about random graphs? That average shortest path in such a graph is short. Okay, so in average, in a random graph, to get from any point to any point, you can in a fast manner. So this is the property which is like for majority of such graphs, if you have enough edges, if they're connected, the shortest path for all possible pairs will be short enough. That's an interesting observation about such kind of graphs. On the other hand, they have a small clustering coefficient. Why it's bad for search? It is bad because imagine that you have neighbors in your building. So you live in dorm, for example, and you have some neighbors. And I'm doing a search in terms of geography. I want people living in the 4th dormitory here. And you are not very friendly. And you don't know your neighbors. So I cannot, using your knowledge, get the contacts of people who live in the neighborhood. So the high clustering coefficient means that if you have the dormitory number 4, everyone knows each other. So cluster coefficient equals 1 means that everyone knows each other in this dorm. So it's called clique. Do you hear about clique in the graph? So when you have the component of a graph, which is fully connected, so everyone knows each other. Yeah, so it's a very strong community. You know each other. Like in your group here, you know each other. Your clustering coefficient is big. If you know only a couple of people, I cannot use your knowledge to fastly find everyone from the neighborhood. So if I ask, for example, I don't know, the sleeping guy in the first row, do you know everyone on your back? You say, I don't know these people, actually. And then I need to go to each of you, Joey.
Yeah, I'd be a good example.
Yeah. At least you know me and I know them.
Yeah.
Okay, so for search of nearest neighbors, this is the bad property. So if I rush into the class and ask, I need all master students of the first year of data science, you say, I don't know these people. Maybe they're just random guys. I don't know you. It's just some people rushed in the room and sitting here listening for some very boring lecture. So one property is good, one property is bad. On the other hand, there is the graph called, the type of graphs called regular. They are not exceptional, so it doesn't mean that random graphs cannot be regular and vice versa. But regular graphs are graphs with the property that the degree of each node is constant. You remember the degree is number of friends. So that means that I know 100 people, you know 100 people, everyone knows 100 people. So this property is good for modeling some uniform networks, like some parts of internet can be modeled with such networks and so on. And of course, these graphs can be random because you can generate such a graph in a random process, intentionally or not intentionally. What is bad about such graphs? They have pretty large diameter. So the longest shortest path is usually pretty long when k is small. But they are very good in clustering. So such graphs are usually, there's the theory, graph theory, the contemporary, and there's a very good person called Andrei Mikhailovich Rygorodsky. It's the researcher from MIPT. Rygorodsky is very good in explaining what is the almost all the graphs. So if you find his lecture in English or in Russian about some graph theory, he usually starts explanation is what does he mean under almost all the graphs. Then when you take the number of nodes, you tend it to infinity, and you do some all possible graphs, and you measure the property of all the graphs. And if the number of graphs which satisfy the property is also tends to 100%, then it means almost all. So I'm not very precise, but the idea is that almost all has some mathematical definition. So almost all the graphs are very good in clustering, but they are not very good in finding the shortest paths. And we go for like 50 years back, and we want to like greet here Stanley Milgram. It's a sociologist who did some very strange experiments with people. He even hit people with electricity. But this is not this experiment. Initially, there were like models of graphs which we used to model societies. I mentioned random graphs were used. Some people said that social graph of people, when we have almost all of us have the same number of friends, like in general, then we can use regular model. And then there should be these properties of society. Or if this is a random graph, then there should be these properties of society. You see that they are slightly opposite. Yeah, so these are slightly opposite definitions. So for one, the average path, for others, shortest path. They are on the other, on the opposite ends of the scale. So sometimes it's good for search, sometimes bad for search. And he decided to check what is actually the society, how it's organized in terms of the graph. Is it a random graph? Is it a regular graph? And so on. And he launched the experiment, which is known as small world experiment, and which ended up with 6 handshakes rule. The experiment was the following. So he took few people from the central United States, so central states. Central means in the middle of nowhere. And he asked these people to address a mail, paper mail, to a person living in Boston. And they didn't know this person. They needed to use their like friendship, people who they know, to try to think about who most probably will be of this friend of this person. Either chance, for example, maybe this person is living in Boston, maybe he is a scientist, maybe he works in MIT, so I should look for a person who teaches mathematics in my hometown. And this kind of guesses were leading these people. They were given some instructions. They needed to do what? They needed to send this paper mail. The person who gets this mail should repeat the operation and proceed with resending the paper mail. The result was interesting, but was criticized by scientists. So big part, I think 2/3 of all the paper mails just disappeared. Obviously, when you do such experiment, someone sends a mail to someone doesn't care, someone is dead. So you just no one checks. I just actually, I'm not checking the paper mail box in my town here in Annapolis, because they usually write you if there's a mail, and then don't bring it to your home. So I just found a mail, like the envelope in my post box from the December. I just opened it to check that if there's something, and there's something laying from December there.
People did use a lot more paper mail though in 1960.
Yeah, I mean that. Yeah, but
they have to use email or something like that. Say, forward this email.
still, this was not that how to say it, guaranteed way of delivery, so that the dog could eat the mail. Okay, and the significant part disappeared, but from those which reached the destination, there were none of them, or at least the small part, who exceeded 6 red cents. Yeah, so it means that you have, at that time, I think, I don't know, 200 million people, 300 million people living in the United States, and only 6 red cents from A to B were enough to send a mail from a person who doesn't know the acceptor, just 6 handshakes. And this was a very interesting observation. So for such a big graph, which is meant to be regular or random, don't want to know, we have this robustly good result. So if the mail reached the destination, 6 handshakes. Wow, very good. And at that time, it was just the matter of publishing a sociological paper. And later, the Watts and Strogatz, mathematicians in the 90s, 1994, I think, they introduced the formal definition for such a graph. So small world network is the graph where most of the vertices are not neighbors. So there is a small mean degree, the sparse graph. So not that many edges, but still there is a small number of hops needed to reach one node from another. And this small was defined as logarithm of n. Okay, typical path length should be a logarithm of n. And it appeared that a lot of networks in our real world actually are better described by such networks. So internet, wiki, social graphs, power grids, they are mostly better described by small world networks rather than by regular or just random graphs. There are some networks which are definitely not that good in describing by small world. For example, if you have many generations of people, so even if I try to build a handshake sequence between me and Jesus Christ, there are many generations which separate us. So I need to pass all these generations, and this will be a long, long walk. Okay, how many generations? 25 years per generation, 2,000 years, 80. So pretty long path. And in case everyone knows each other, so there is a handshake path, the shortest through the generations. Classmates. Usually you know your classmates, but you don't communicate with people year older and year younger. So that's why your graph is the stratized. There are some well-defined clusters, and there are no connections between the clusters. If you ever visited your school after graduation and you see these portraits on the wall, who are these people? So I know these guys because these are just random people. Okay, and these two guys first, and then Kleinberg, they introduced some procedures of building such graphs. So they said, we know how to construct such a graph. Why this is important? I don't know how pure mathematics is working in your brain, but for me, I explain it like this. Imagine you want to model something about our society. Okay, previously you used the bad model. That's why you get very bad predictions. So if you build the 200 million random graph, 200 million vertices random graph, and you try to predict some properties, how, for example, the news are spread through the American society, or how the virus is spread, you will use this model, and this model will be bad in predictions. Now you have the better model, but you cannot just take all the people in the United States and ask them who you know. We usually do this once in 10 years. It's called census. In Russian, it's called перепись населения. But unfortunately, you cannot do it like each time you need to do experiment. So that's why you need to model. You need to generate a graph with similar properties and run experiment on this graph. And if you can do it in a better way, if you know how to construct a graph which is by properties very similar to the society, then you are very close to good predictions. So that's why these processes were very important. Actually, the algorithm of Watson-Strogatz was very simple. You take a regular graph and you take the probabilistic process. You build a regular lattice and then you rewire some nodes. So you tier some connections and rewire them to some very random distant people. This is how actually we live here in our world. Usually we know our neighbors, yeah, but also we have, I don't know, I have an aunt in the United States, I have a friend in Barcelona, I have a friend in Canada. There are a very small number of them. So a few countries, maybe a lot of countries, maybe 20, 30 countries, but only one person in each. But these long range directions are very useful because if I want to build a sequence of handshakes to the Queen of England, of Great Britain, sorry, Joey, then I have a friend who just got the citizenship of United Kingdom. So it means that he met someone from authority. That means that authority definitely have a couple of bosses, which end up with prime minister, who definitely met Queen Elizabeth.
And because of that, you also have the pathway to Putin, because you know Minihana.
My path to Putin is much shorter than through Minihana, you know. Okay, so this is the process. So you cut some neighborhood connections. You maybe I don't know him, but I know a person in United Kingdom, and that makes it possible to track a path from me to the Queen. Okay, still, I'm giving you some insights about the way how it works. And what I use very geographical intuition, yeah. But in graphs, for an edge, there is no need to be like somehow related to distance. So edge is just a connection. So some friendship, something. No notion of distance yet. Okay. So graph should not be weighted. Here you see in this model no ideas about the distance, only the structure of the graph. And this is an important thing. So these graphs, the previous graphs, are just vertices and edges, objects and connections. You can display it in multiple different ways on the plane, they will be still the same graphs. But if you embed a graph into the metric space, what does it mean? That for every pair of vertices, you introduce the distance with no difference. Are they connected by the edge or not? So now we have both distances and edges. Okay, that's very important. In Russian, we don't have such a term, so there is no proximity graph. In Russian, there is term метризированные графы. They are exactly about embedding graph into metric space. In English, there is a term proximity graph, which also requires some more. Okay, so this is a graph embedded in the metric space, plus that it should tend to create edges between the nodes which are close in the metric space. Okay, so in this picture, you will not see the edge like this. Okay, because the graph tries to preserve the neighborhood. So the edges are mostly in the neighborhood. And there are many such graphs. So do I have the names for them here? Yeah. Relative neighborhood graphs. This is one. This one is relative neighborhood graph. Actually, Donut triangulation is the proximity graph. Gabriel's graphs. Minimum spanning tree is also a type of proximity graph. So they are multiple of them. So, but the idea is that still, it's very important to know that graph can also have a metric. So previously we spoke about edges only. Now we can compute the distance between these two nodes in the notion of, for example, Euclidean distance, not by the number of edges, not by the sum of lengths of edges, but the Euclidean distance. Okay, and this ended up with the idea which was presented by Malkov and Yeshunin in 2013. They said, let's take small world graph and put it into the metric space. So we introduced the notion of distance between any query, which can be a new node for the graph. So we even don't know whether this vertex is present or not, but we can put it somewhere into the space. So here we draw a graph in two-dimensional space. So we can say that this is the two-dimensional space, and there are some coordinates, some vector representing the node. And they proposed the following idea. So what if we do a greedy search? What if we take any random vertex from a graph, and we will greedily traverse the graph towards the query? So we start from here, and we want to find the closest out of our neighbors in terms of edges, which is closest in Euclidean distance to the query. So out of this, and this friend, this one is closer. Okay, and we go there, and we repeat. So for friends of this, who is the closest? This one is closest. Okay, we jump here. From friends of this one. Okay, this is the method which is called beam tracing, ray tracing, like the algorithm when you try to, or ray casting algorithm. So you want to go somewhere and you do it greedily. And what is beautiful about the structure, that they said that we propose the building procedure, which is uniform for search and for creation. So the procedure is very simple. You do search. You find nearest neighbors for the next inserted vertex. And when you find these neighbors, you connect. Then you take another vertex, you insert, you connect. Okay? Why? And they observed that the result of this procedure is actually the small world graph. So in terms of the graph, it's small world graph. Why so? Because when you insert in the very beginning, if your nodes are random, in the beginning of construction, you build long range connections. So if you insert 4 points located in very distant positions, and you will wire them first. And then further you move, the closer neighbors will appear. Okay, so the nature of building, of the procedure of construction, is that it creates first long range and then short range connections. And search is actually greedy one. So you start from somewhere and you travel to the query. Actually, this is very like approximate explanation. I have, I think, a very good visualization in my Instagram, so I'll show it here. I hope it will be pretty understandable. So you not just travel through the space, you also take a gang with you. So there's a gang of friends who are surrounding you and who are also examining their friends. So not me only searching for the shortest path, but also Joey, as he has very random people in his neighborhood, like I don't know them. We together can succeed much more in searching our shortest path together. And you see how some outliers appear on the path. So some very random nodes covering very big area here help us to get the query. And of course, the notion of search is not just the idea of search, sorry, is not just to get the query, okay? Because it can appear that this query is not a part of the data set. But we are interested in the neighborhood. That's why you see it when it reached the query, it sometimes jump around. So the task is to find all the closest friends and to return not the single query item, which can be not present, but some number of relatives, some friends, which are closest. And then this will be the candidates for pre-ranking set. Okay. So this is the like I think the best explanation which is possible. So you just see how it works in terms of Euclidean distance and in two-dimensional vector space. Oh, boom, boom, boom. Okay. So this is the graph. We have, I think, 3 minutes left before the break. The next idea, the next iteration here was that, obviously here is what is important, that they didn't prove it in their work. They showed it only by experiment. It was proven by Yandex researchers in 2020 that still, if you run remember the shortest path in such graph is expected logarithm of n, but their algorithm is greedy. It doesn't guarantee the shortest path. It just approximates the shortest path. But still, it is proven by Yandex researchers in last year that still the search time in such graph is also expected logarithm of n. So they didn't exceed this limit. And the next step of the same research group was to build a hierarchy upon. So they build a navigable small world on the first layer, and they do some kind of, hubs for this graph on the next layer. So just imagine you have the road network on the first layer. So all the cities are somehow connected. There are highways connecting, let's say, Kazan to Moscow, which you can travel for 10 hours and you get to Moscow. But also you'll spend 10 hours to travel to some Moriel village because the road is very complex. But there are hubs, the connection of big important nodes with the highest degree, which are easy to travel. So just airports: Kazan, Moscow, Voronezh, St. Petersburg. I don't know which airport you prefer.
With me, it's usually to Istanbul on to Toronto.
Okay. Istanbul and Toronto. And this is the network, which is much smaller, but which allows you to fastly jump into the neighborhood. So you travel from Toronto to Istanbul and to Kazan, and then you go down and you travel by taxi, okay, by a slower mean of transportation. And if you build few layers, this is logarithmically decreasing number of edges. So it's usually only few edges. So for approximately 1 million of nodes, we had, I think, four layer of such network in our practice. And then you still can do logarithm approximation, but in practice, like in real computations, it's much faster. And it appears that this approach is, for now, is the state of the art in the time of practical speed of search. What is important here, that even if I mostly explain this on coordinates and vectors, this graph doesn't care about vector representation. So you can have any metric. So if you can build a metric, that doesn't mean that you need a vector. So no need a numerical representation for your documents. If you can compute a metric, you can build a HNSW graph for the words, for Levenstein distance, or for editorial distance, whatever. No embeddings, no vectors are required. Still, they are most widely used here to represent the documents. Okay, and I think if you want to extend your knowledge, you can read the next introduction to proximity graphs to know about them better. So which kind of graphs do exist. And also there is the latest paper, like the last paper about the data structures, not the last on this topic, where you can learn about how to construct hierarchical navigable small world. If you have any questions on this topic, you can ask them now. If no, we will continue in 10 minutes. Let's say 10:51. You can have your coffee. A question from the offline, okay?
So you have given an example of refrigerator here. I cannot understand how you can with searching online and this thing.
How?
how they're connected.
How they connected? Okay, yeah. So maybe the connection was not that obvious. So the guy was doing an index for advertisement. So there are like millions of advertisements, and they need to be accessed. They indexed by some vectors. So meaning that these are about refrigerators, these are about cat food, these are about so on. So and when the image is displayed here, you need to be very fast in showing the advertisement connected to this image. And to do this, what is happening? So first you go search for an image, and this is what is search engine is doing. But the second step is to, by giving this image, to search in the commercials, the advertisement index, and to retrieve commercials which will be with a high chance clicked by a user because they will be relevant. And in his project, he decided to try this way of indexing given a vector representation for commercials, for advertisements. Is it clear? Wonderful. So guys, 10 minutes break. See you in 10 minutes.
Okay, thank you.
Okay, guys. I think we can start with attendance check. I will be doing slowly to make others return. Don't think I forgot about this. Attendance. Shuch. Pum, 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 pum. Muhammad, here. Ayomide, online. Kirill, тут. Adel Queen, not present. Денис Фокин. Хадиджа, here, online. Роман Гараев, здесь, да. Вайгу, here. Ikram, I saw her at the first lecture. Let's wait. Firas. Елизавета. Далер. Академик Лив. Yeah? Ярослав. Герман. Мы их потеряли. Айдар. Данил.
Yeah.
Okay. So some question only about Ikram. She was present, but not here now. Okay, let's recheck later. Save attendance. Okay, let's go. An hour and a half of boring things. Let's do it fastly. I'll try to attract your attention, but I can't guarantee it. So you remember that, I hope you remember that I started the previous lecture with a overview of 4 different approaches to indexing data in a vector representation. First, we considered clustering of vectors and building some either hierarchy or inverted index based on clusters. Second, we actually didn't utilize vectors, we tried graphs, and we just took the metric space. And for vectors, it's easy because vectors are usually meant to be in vector space. It is not guaranteed, but we assume that in majority of applications, it works like this. And this lecture, I will speak about trees, different types of search trees, how they evolved and how they help you to search for nearest neighbors. What was the problem? One of the problems which I will mention right now, that everything is good about HNSW. It's very fast. It's logarithmically fast for the data. Unfortunately, it guarantees only expected time, meaning that there can be a user, there is a chance for a user to wait for the result for a long time. Yeah, so it's either you pay more time for searching because expected time is logarithmic, but for a particular query, it can be unlucky chance to start from the wrong node and you'd spend a lot of time for searching neighbors. Or if you have some limit on maximum number of hops in the graph, so you limit the length of the path, the result can be irrelevant. So either this or this. So expected means there are some cases which can slightly what's called degrade your quality. For trees, it's slightly better because we will speak about search trees in general, some particular trees, and see that initially the first idea behind search trees is to guarantee logarithmic time. So sometimes they are better in this case. So first we will start with search trees in general, then quad trees, and so on, so on, so on, so on. I think as soon as we finish, we can. So search trees, search trees, search trees. What are they? Let's refresh. who can say what is a search tree? What's the idea behind any search tree? First of all, what do we search in search tree?
Vertices.
Vertices. Like no nodes, sometimes leaves, sometimes not. But I mean that the nature of data, which we discuss in the course of algorithms and when we speak about search trees, is scalar with with an operation of order. Yeah. So what can be the key in a search tree? It can be either a number, yeah, floating point value, integer value, doesn't matter, and something with an order, a tuple, a word, whatever. Okay, whatever can be ordered, and this order has some meaning for us. So if we put numbers in the search tree, in the leaf nodes, they will be ordered increasingly. If we put words in a search tree, in the leaf nodes, they will be ordered alphabetically. Okay, so there is some semantics behind this order operation. Okay, but if we put something more complex, sometimes things are not just ordered by nature. So is there an order for pieces on a chessboard or cells on the chessboard? Is an order for you? If I put you in the search tree, who should come first and who should come last? Which property is the most important in your case? One of you is seen, one of you can solve equations, one of you sleep 12 hours per day. So which property is the most important for ordering people? We don't know. So the trees are naturally work with scalars. Then, if you remember, there are some types of search trees. Some of them are, most of them are k-array. So the most widely known are binary trees. Okay, where k equals 2. So binary means what? Each node, as in this picture, can have not more than 2 children. Okay, there are some limitations for different nodes. For example, some nodes can have either 0 or 2 children. Some of them are allowed to have 1 children and one child. This can be different, but the idea is that binary tree allows splitting by 2. So why it's important to limit the number of nodes in the tree by some number? No, yeah, so it can be a tree like this. Yeah, and it means that if you want to find a child, you will need to scan through all possible opportunities. And this is actually the generalization of idea of clustering. You remember that I said that you can do hierarchical clustering. So, and depending on this initial size, you remember that approach which my colleague showed, he chose square root of n. Okay, and if we increase the number of levels, we decrease the number of elements in each level, we can do even better. So the smaller the cluster, the better is approximation. And if we move it to the optimal thing, we will see that the optimal situation, if we fix the size of the cluster, and then the number of layers will be proportional to the logarithm of the number of elements. And it doesn't mean how many is the constant. If the constant is 2, this will be a logarithm of 2. If the constant is 10, it will be a logarithm of 10. But the logarithm, like the base of logarithm, can be changed by a constant. Okay, and that means that we can vary here this k parameter to achieve different properties which are important for us. For example, for binary tree, what we say, binary tree is one which is very fast in selecting the direction. So we do logarithm number of comparisons, and that's perfect. The depth of such tree is log 2 of n. Okay, where n is the number of nodes, which number of numbers, number of scalars you want to index. Is it good to have logarithm 2 of n? What if we have logarithm 10 of n? What will be different? There will be 10 children, but the more shallow tree. So logarithm 2 of 1000 is approximately 10. Logarithm 10 of 1000 is approximately 3. Exactly 3, sorry. It means that if we speak in these terms, that in the tree with 10 children, there will be only 3 layers. In the tree with 2 children, there will be 10 layers. Okay, 10 levels. And so it's not that different in terms of absolute values. 3 and 10 are both small numbers. But in terms of random memory access, for example, that's very important. And again, in the algorithms course, you may be told that using these binary search data structures, it's very good to do in RAM. So computations are very small number of computations, and you just jump in the memory and find the result. But each such operation is a random change of memory position by default. Okay, so you move from one position to another, and in RAM this can be very distant places in your computer in memory. And this is very bad when your tree is stored on the hard drive. And are there such trees which are stored on the hard drive? Who knows? Do we store trees on the hard drive sometimes?
File system.
Yes.
Yeah, file system maybe, but the most obvious example, if you speak about indexing, so there are indices in file system, but the most important thing which is studied usually in the very first years of education are databases. In database, when you index the column, for example, by string or by number, you build an index, and one of the most ancient data structures which evolved significantly since that time is B-tree. B-tree is the tree with a large number of children on each node. And B-tree has evolved into B star, B plus, LSM, LSM epsilon, wow, that many number of trees, but with the general idea, they are stored on a hard drive. And when you use hard drive, especially when we speak about hard drives which use rotating elements, the old ones, very, very big in terms of possibilities of storing the data, accessing the memory is a very expensive operation. Accessing the position on the hard drive is expensive. That's why when we read RAM, we read just a small number of values. But when you read hard drive, you read the block, which can be 4 kilobytes of memory. Usually, you read not a single byte, you read just some bunch of numbers. And that's very cool to store these values of the size which is comparable to a block. Okay, it's good to have a key which is stored, or the number of keys which are stored sequentially on the hard drive. And for a hard drive, this operation becomes very expensive, and this operation comparatively cheap. So reading one key and reading 4 keys at a time and 4,000 keys at a time is equally expensive for reading from the hard drive. So better read more. But changing the location of the header, with the spinner, which like how to call it, header, which is reading the data on the rotating magnet disk in the hard drive, is very expensive. That's why making bigger size of children, making search shallower, so that reads shallower, is important to preserve the speed property. Okay, they all have the similar procedure of building and procedure of search. If you know that your task is to partition the sequence of elements into some blocks, what you do, you choose one of the directions which satisfies your condition, and then you move to the leaf node to see if you search here for, let's say, 37 37 in this tree, you will choose this range. Then you will choose this range after 21. Here you will choose to scan through and find that 37 is between 27 and 38 and it's not present. Yeah, so your search will be pretty fast. It consists of scans through the keys and following the arrow. The same for binary search tree. You go either here, either here, either here, either here, and so on. All these trees, especially the trees which have the self-balancing properties like AVL trees or red and black trees, they are guaranteeing you by the nature of data structure logarithmic time, no matter how many elements did you insert and remove from this tree. Okay, they're very cool in self-balancing, and also they can be homogeneous and non-homogeneous. What does it mean? Homogeneous means that all important data is stored throughout the whole tree. So AVL tree is homogeneous, meaning that leaf nodes and internal nodes, they all are important. So the document which you're searching for can be in any position. It can be here, it can be here, it can be here. For B trees, that's obvious that the situation is opposite. All important values are stored here, and everything which is on top is just a supporting construction. So you use them for search, but what you want to obtain is on the lower level. Okay, this is the difference: homogeneous, non-homogeneous, but all of them guarantee you logarithmic search time. Whew. We did it. And what about the vectors? As I mentioned, for scalars with the order operation, we can build search tree. For scalars without, so for any objects without, that's not that obvious. How should we decide in which branch of your search tree should you put the value? And the answer originated from computer graphics. Computer graphics has a lot of tasks with rendering. Rendering is the drawing something, yeah? So drawing 3D objects in 2D. An important task in rendering is not to draw what is not shown. Yeah, so it's very important not to spend your computations on the scenes, parts of your scene, which are not here, which are occluded. And in this case, you should be able to fastly identify which elements are present in the scene, which are outside of your field of view or occluded by some objects, and some overlapping regions, fully hidden objects, they should be here. Ray tracing, again, so the middle picture, if you want to be very good in modeling the reflections, you send a lot of rays, and of course, you want to minimize the number, so you need to use some kind of heuristics and mathematical justifications of which rays you should not even model, which will never return to you. So being able to save computation in some multi-dimensional space, meaning 2 and 3D, is very important. So it originated from computer graphics, and it gave us few interesting data structures. So, of course, as I also spent some time on explaining the binary tree. So if you consider the how to say it, the degenerate case, if the vector consists of a single dimension, we can go for these display arbitrary AVL trees which are stored in RAM, for B trees, LSM trees stored in hard drives, and the search, the different procedures of search can be conducted fastly. Search for exact element, it's logarithm of n. So that's usually what we consider in algorithms course. If we want to search for k nearest neighbors, what we do, we search for an element, and we scan through the tree to the left and to the right. And maybe you remember that there's a proof and there are some observations that scanning through the tree is a linear operation. So if you traverse the tree in increasing order or decreasing order, you do it in linear time. So if you search for k nearest neighbors, it will be logarithm of n to search and k operations to search your neighbors. If you do a range search, again, you start scanning to the left and to the right from the middle, or if you start from the beginning of the range, you move through the tree to obtain the other side of the range, and you do it in linear time with respect to the size of the range. Okay, so these are trivial cases. And what about indexing two-dimensional data? And the first idea came long ago, 1974. It was called quad-tree. The idea of quad-tree was then developed into multiple exact implementations. So it was done for regions, points, edges, polygons, and so on. And all of them share the same ideas. So first of all, we try to decompose our space into adaptive cells, which are the different sizes. You see on the picture that some cells are big, some are small. This is all done to be able to make the tree shallow enough. And each cell is limited by maximum capacity, so it can store up to some number of points. But if you exceed, you can split the node into parts. And when the node exceeds capacity, you split it into 4 regions. That's why it's called quad-tree. So you see each time if you look at any square, it's either like just solid or split into 4 parts. And what about ideas behind quad-tree? Quad-tree says the following. So we will take our space, build it, like decompose it into 4 regions, and see whether this region exceeds the capacity. Okay. Then, if it exceeds, we split it into 4 different regions and check any of them for exceeding the capacity, and so on. So that here you see it's only 2-dimensional case. That's why, for example, these quarters will be called, for example, northwest, southwest, northeast, southwest, and southeast. That's how they are denoted in the original algorithm. And of course, search is pretty obvious here. So this is again the search tree. Instead of comparing with one value, you understand at which quadrant your value falls. So if you need to go to the southeast, you go to southeast. If you need to go to northwest, you need to go to northwest branch, and then you search in this branch. The algorithm of query range, range query is the following. So you want to cover some range, and you see which quadrants actually fall into this range, which not, and which lay on the border. Okay, and just here, I think you can read it later. So very simple. If you construct the result, the points in range, you do what? You see that actually the boundary of your range intersects with the boundary of the quadrant. If they intersect, then you return points. Otherwise, not intersects. If it's included, you go here. If it's not included, you return nothing. If it intersects, you check the points of being in range or not being in range. And what is important here? So insertion is managing capacity. So you will maybe reuse it in your homework, the idea. So just understand that if you add a cell, oh sorry, add a point to a cell which now exceeds the capacity, you will need to split it into 4 parts, and that's it. Some non-important information actually. So why I'm telling you this? You can read the code by yourself. Just quad tree. What's wrong with quad tree? Quad tree doesn't define anything related to the fact that the data is distributed somehow non-uniformly. What if all the data is concentrated in the single corner? You start with some range, and then you have 4 big quadrants, and then you dig very deeply in your tree, so it can be a degenerate tree with all the nodes in this quadrant. So you will go deeper, 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 because a lot of points are concentrated here. Okay, you understand that this will lead to imbalance. Okay, so the tree will be in some cases searched fastly, in some cases for a long time. And they try to deal with this at the insertion stage. And these are pictures from the original page, which tried to show how can be the branches of the tree reorganized in case you observe this situation. For example, you see that there are big quadrants here, and there is also divided quadrant and also divided quadrant. So you see that these are 2 levels lower than this. So this is, for example, the first layer. This is the 3rd layer of the tree. And they say, let's change the order. Okay, let's then B become the first order center. So we slightly move the borders, and we will then balance our subtrees to have only difference of 1. Okay, what if we have something like this? Again, procedure which changes the order. C was the leaf node here, B internal, A root. So B now is the root. Here C was the leaf node, now C is the root. Okay, does it remind you anything? No, it's very similar to balancing operations, which are called left and right rotations in AVL trees. This is actually exactly the same as AVL tree rotations. If you had AVL trees in your algorithms courses. Okay, so AVL tree, it's I assume that you know what is this. AVL tree is the tree proposed by Adelson, Velsky, and Landis in 2062. Binary search trees were invented in 2060. So what's the difference? Binary search tree is just an idea that you can take the data and build a binary search tree upon the data. AVL tree was the first data structure which was self-balancing, means that they didn't care. Do you insert the nodes? Do you remove the nodes? It will always guarantee you logarithmic time of search. It's a very cool idea. So if you just imagine any binary tree, if you remove something, it can become degenerate tree. So it will be very good tree, like this, like a fir tree, but then you cut this part, and your tree becomes just a list. So whatever remains here is a degenerate tree. Yeah, it takes time, but this time is also logarithmic. So it means that if you insert a node, it takes one logarithm time for search, logarithm time for rebuilding, and all in all together it's log plus log logarithm time. So yeah, it takes practical time, but asymptotics, the complexity is logarithmic still. They tried to do it in quad tree, but they show that unfortunately this cannot be that efficient. So it cannot guarantee you logarithmic time still. And second thing that they even state this fact in the paper, that unfortunately there cannot be better choice for the data structure which requires a lot of insertions and deletions, then at what time take everything out and rebuild the tree in the end. It's a pity, but still we still live in the world of search trees
which are on a large scale not that good at self-balancing. And this is the matter why a lot of data structures which are used for indexing, they are not usually updated. So you build a big index, you store it for a long time, for a week, for a month, and you store the fast diff updated. So for example, search index of Yandex stored on the hard drives on big number of machines, and also the fresh index, which displays the changes of internet for the last days, minutes, and so on. Also, there was an optimization, which at least at the building stage could guarantee you logarithmic time. And this optimization was the following. Instead of taking a predefined range of values and splitting the space into equal quadrants, let's do it in the way that at least, at most half of the nodes will fall into one cell. So we should limit our cells in the way that at most half will be in one cell. So for example, if previously we were in the world where this was legal, yeah. So for now they say no, we will build the quad tree in the way that it will be like this. So the coordinates of the center will be chosen with respect to the data. So previously it was chosen with respect to the coordinates of the world. You can send it to me, and I don't know. Oh yeah. You can do it and see it, but the idea is that now we can do adaptive cells, so they will adapt to the data. And the worst case which can happen if the data is distributed like this. So each time you split it into 4 parts, these 2 will be empty, and these 2 will hold the half of the nodes. Yeah, so this is the worst case. In better cases, there will be more fair distribution. Okay, so this is the way of building a tree, which at the construction phase can guarantee you logarithmic time. So quad tree was an important invention here. What about suboptimality? Obviously, they are the following. So first suboptimality, empty cells. Have empty cells. Why should we store some memory for empty objects here? Second, why do we stuck to northeast, northwest, and so on? So why, if we have these data, we need to split it into 4 blocks where 2 will be empty, rather than to splitting them into, for example, 4 blocks of equal size? So who said that we cannot take south, east, north, and west? So why we should align with these coordinates? Why 4? Why not 3, 6, 8, 17? The more children, the shallower is the tree, the less operations you need to do. And also, why only 2 dimensions? So all these questions are asked and challenged quad trees. And then some answers for these questions appeared. And the first and one of the most powerful things today, still today, because if you will go for an interview to Yandex, they will ask you the question about the data structure. It is called k-dimensional tree, KD tree. It was invented only a year after quad tree, and it was trying to answer at least the part of the questions to quad tree. So first of all, as you see, k-dimensional tree has k in the name, meaning that we can put any k here. So k3, okay, k4, okay, k2 also can work. So it splits, then it splits each time the subspace not into 4 parts, but in 2. And that means that you can always guarantee that the data can be separated into 2 equal parts. So there will be no empty cells here, no empty children. And to be able to split the space somehow fairly, we do alternating coordinates. So how it works? So I think I have an example here. Yeah. So let's think about construction of. Do I have any other beautiful pictures? No, this was one. Okay, let's speak about building a about homogeneous tree. You remember homogeneous, which stores the elements in the nodes, okay, in any nodes. And non-homogeneous only in the leaf nodes. So how KD tree is working in terms of two-dimensional case? So alternating coordinates, meaning that we will each time consider next coordinate, next. So for two-dimensional case, we start with x and then y, and then again x, and then y. So let's start with x. First, what we do, we sort the data along this coordinate. So we take only x coordinate and we sort the data along this coordinate. And then we take the median value of this data. So in case it will be a homogeneous tree, we will search for a median value and put this value into the root node, okay? And we will split the space into those which are less than this median value by the first coordinate and which are bigger. So these are less, these are bigger. Okay, so we found this 7, 2 point, which will go here. Okay, and then for each subspace, so let me change the color. For each subspace, we repeat the operation. So for example, let's consider the left subspace. So in left subspace, we have 1, 2, 3 points, and the median value is here. Okay, and we use it to represent the border between the subspaces. And we put this into the left branch of our tree. And then we sort them on those which are bigger and those which are less. Okay? Okay. And then, for example, if we expand this branch further, we consider the this subspace. So let me draw the border now, this subspace. Okay, and in this subspace we also change the next coordinate, but we have no more coordinates, so we used x and we used y. So now we will reuse x again. Okay, and for one remaining element, it will become the median. So we will put it into the leaf node here. For the other subspace, so again, so we have this one go into the root. Right subspace consists of 2 elements. Let's say the median will be this one. It splits the space into those which are bigger and these are less. And this one will fall into the less branch. Okay. That's how the k-dimensional tree is built. So first, by selecting the median element, we guarantee that we are almost splitting, like almost always, split it by halves. Okay, so it splits into 2 parts. Means that by construction, this is a logarithmically deep tree. So it's not more than logarithm of n. So yeah, but it's divided horizontally, vertically. But each time you divide the space by 2 parts, and the number of elements in each part is half of the elements, at most half of the elements. That means that in logarithm divisions, you will end up with 1. Okay, that's why it's the depth of the tree is logarithmic.
How do you define median?
What is median? You tell me. What is median? So you sort the data and you choose the middle one. That's how you define the median. So are there any definitions? Any other definitions for median?
There is no need to sort.
No, yeah, you can search for kth order statistics, but yeah, I mean that to define the median, it's the value which is more than half and less than other half. Cool demo. So let's click. I have the link to cool demo. I don't remember what's here. Oh, 6 minutes. No, we will not watch.
Welcome back to the video lecture series.
So, oh yeah, it's the guy who uses software, and he shows. You can look at home. So how the tree changes by adding
We're not limited to just tutoring better children.
adding more and more. Well, yeah. So yeah.
The way that I'm building my tree here, I am putting the cut along the dimension
Just
that
watch
has
it at
the
home.
spread. So if I put my 2 dots there,
Yeah. So this is just a demo of how the tree changes with respect to the data. And you see that it adopts the size of the cell to the concentration, like to the density of points. Okay, so this is the picture with example of building. This is how the tree can be used in graphics. So to store the points belonging to some object, it can be denser, as I mentioned, in dense points, the smaller nodes, and the bigger nodes when there's nothing. Here is the implementation, which I propose you to look at before you implement the homework, because this is the simple way of obtaining the median. So here, what I want to highlight here that yeah, selection algorithm, which is mentioned by Daniil, is allowing to search for a median element without sorting in a linear time. The problem here is that median is the problematic value if you have duplicate values of the same coordinate. So if you have all the points with the same coordinate, you will be in a bad situation, because you need to either split the points with the same coordinate into the different subspaces, which is unacceptable because it will influence the search quality. Okay, so if you run into the median, which branch should you choose? Or you should do some not optimal division of points. So you should choose the smallest median or biggest median value. So the smallest by index value, which is equal to median by value. So if you have the index like 1, 2, 3, 3, 3, 3, 3, 4, 5, the median value is here, but you need to use this one. It will split the tree into non-equal parts. Okay, you understand that this is a problem of choosing the median. So that's why you should always consider the data. Is it possible? Is it the case in your case? So if you use integers, it's highly possible. If you use floating point values, this is low chance. So you can say that I don't care about the situation. Then still you should not be very strongly worrying about this, because if there are no full duplicates in your data set, even splitting like this will split these elements at the next iteration by another coordinate. So if they are not fully duplicated by all the coordinates, at least at one dimension, they will be split. Yes, it can bring you additional depth to the tree, but they will definitely one day fall into parts. So if there are not full duplicates. So you can use this as the starting point, but improve it later for your homework. So this is how to build a homogeneous tree. So you take the median, store it into the node, and then for left and right parts, build k-dimensional tree and store them in subtrees. What are the characteristics? Build time is fast, pretty fast. Requires linear overhead for memory, so k for dimensions and for number of elements. So no significant overhead with growing of data set. Range search depends on the result size and on number of dimensions. The bigger is the number of dimensions, the closer is range search to just n, to linear search. The smaller the number of dimension is the better. And one nearest neighbor search is very fast. The one which is actually useful for computer graphics. If you want to find a particular thing here, is linearly fast. The difference between k-dimensional trees and HNSW is that here you must have vector representation. Okay, that's obvious. So vector representation here is important, and it's both important to have notion of distance, because you look to search for nearest neighbors, for example, and the notion of vector to be able to split by coordinates. Next thing, which is not mentioned in this slide, but is very important to know and understand, that if you have 1 billion of elements in a tree, which is a pretty big number. Yeah, big. Okay, I hope you agree that 1 billion is still a big number. And you do a binary tree. So k-dimension tree is binary. Each time it splits by 2. So the depth in the best case is a logarithm of 1 billion with a base of 2. Okay, which is, if you remember, we counted that the logarithm of 1000 is around 10. Yeah, slightly less than 10. So then the logarithm of 1 billion will be around 30. Just mathematics, ninth year of education in school, logarithms. Yeah, so the depth of such tree will be of 30 levels. Okay, if we follow the procedure of KG tree, we will do what? We will use the first coordinate, then the second, then the third, and up to 30th coordinate to split the space. Yeah. There is a term in data science called curse of dimensionality. You must have heard this term. This is usually the term which is used in any case when you deal with multi-dimensional data. So here, the curse of dimensionality works as the following. What if your data has 200 coordinates? What if your vectors representing your data is pretty long? That means that out of these 200 values, only this part will be used for indexing, and these coordinates will be not considered at all. And if you will search for nearest neighbors, there's a high chance that they will be not even in this branch, because they are nearest by this set of coordinates, but maybe the real nearest neighbors are hidden here, because these coordinates will be much closer and these will be different. So unfortunately, for the dimensionality of data, which is high, even for a big number of elements, KD trees are useless. So if you want to build a fast search index for text embeddings of 300 dimensions, and you use KD tree, which is like guaranteeing you to search fastly, you will have just an awful result of quality. They will return you some random results because they will utilize only the first 30 dimensions, not all the dimensions of the vector. And KD trees, they are very good in geography, computer graphics, and so on, where the number of dimensions is very small. But they stop working in the dozens of dimensions. Okay, even theoretically, they are very cool. Okay, let's go further. To build faster range queries, you remember that range queries here can result in linear time. There are some specific data structures which were created to support range queries. For one-dimensional case, range trees, which were invented slightly after KD trees and quad trees, were just a single fix to binary search trees, with the only idea that the node here, instead of storing the separator of the space, stores the the leftmost coordinate of the section of the range. And it means that you can find this one fastly, you can find the second range part of the range fastly, and everything which is here will be in the range. So the very fast way of searching in the range. And there is a generalization of range trees for multidimensional case, where you build the range tree for a first dimension as an k-dimensional tree. Then you take each node and you build a range tree inside this node for a second dimension. It becomes very huge data structure, which holds tree inside the tree, inside the tree, inside the tree, inside the tree. It looks, I cannot even display it. It looks like this. So you see that this is the tree, and inside the node, there is again a search tree. For the nodes which fall here, they will be put into another search tree. And for this node, if you have a three-dimensional case, not two-dimensional, you will have another tree which will represent the subtrees here. So, but still, you see that searching for a range in logarithmic time, and if you have multi-dimensional range, it will have logarithm plus logarithm plus logarithm. So it will be k, where the k is the number of dimensions, by logarithm of n, where logarithm of n is the number of elements. So pretty fast, even very memory consuming thing. And it's very hard to actually store this in the mind. So it's very mind-blowing data structure. And this is the boring thing. So these data structures are very, how to say it, they are very conventional, very good algorithmists of past. They were creating such things. And what if we don't care about this sorting, selecting media, and so if we do some random stuff? And actually, 25, I think, years ago, there were two very good mathematicians, Johnson and Lindenstrauss, who proved an interesting lemma. This is a lemma called Johnson-Lindenstrauss lemma in English. In Russian, it's called the lemma о малых искажениях. So it says the following. If we have the big data set of high dimensions, we can prepare a low distortion embeddings, where low distortion means the following, which is the following thing which is below. And if we do some right things, random projections, so meaning that we choose random hyperspaces in this multidimensional space, and do projections on this hyperspace. So randomly, no procedure, just random projections. Then, following this lemma, we can still get a low distortion embeddings. So meaning that the dimensionality reduction will bring us pretty good approximation, preserving Euclidean distance, which is actually good for us. And they stated that if we want this balance parameter, epsilon, the error parameter, defined from 0 to 1, for a set of m points, so m is, for example, 1 billion here, okay, big number of documents, then we can use n-dimensional approximation, so small n, which is proportional to what? It's proportional to logarithm of m, the size of the data set, and the error coefficient squared. Then it does what? It says that the pairwise distance between projections falls into the range of minus epsilon percent plus epsilon percent of original distance. So it's hard to understand. But again, you have some metric space, you have some high dimensional vectors. we say that there is a procedure which can embed with the following property. What's the property? If previously your distance was 1000 and you fix epsilon as 10%, okay? So you are okay with an error of 10% in estimating the distance. So it means that what? Your new distance will be, so distance is not 1000 anymore, it's between 10% of 1000 is between 900 and 1100, okay? So it falls in this range. Then you can take how many? 8 by natural logarithm of n, which is, who can compute natural logarithm of 1 billion fastly? You have calculator? Oh, I can do this. Calculator. 20. 20. Okay, 20 by 20, 21. Okay, divided by 10% squared, so it's 0, 0, 1. So it means 160 multiplied by 100. It's around 160. These number of dimensions, which can guarantee you that your estimation will fall into this range. Not very impressive, yeah. 16,000 dimensions is a pretty long vector representation. But first, this is guarantee. It doesn't mean that if you take n smaller, it will be that bad. It means only that it will not be guaranteeing anything. And second, that the beauty of this formula is that, do you see n here in the formula? No? Actually, if your original dimensionality is anyhow big, the size of the latent space, the hidden space, which we can use for approximation, depends only on the error size and the dataset size. And it depends on the dataset size logarithmically. For me, it sounds wow, because like we say that we know the embedding procedure, which preserves Euclidean distance, almost the same, and we don't care about original dimensionality. We just care about the size of the dataset. The bigger the size of the dataset, the more dimensions we need. If we could have here a small number, it will be almost nothing. The idea of this lemma is to allow such methods as random projections be supported by theory. Okay, so if previously we said we use random projections to just somehow approximate the vectors, now we can say we can even guarantee something about this. Okay, some size of the error, we can, maybe it will be twice. Okay, 50%. Given 50%, it will be what? It will be 16 by, also 20 by 8 by 4. Yeah, so it's now it's 32 by 20, 604. So changing the Euclidean distance only twice, so the variation twice, you can use 640 dimensions for the vector for the same 1 billion data set. And for example, if we search for nearest neighbors and we don't care about the order in the close neighborhood, maybe it's enough to approximate 3,000 dimensional vectors. You reduce them 5 times. And this is about random projections and about embedding, but we are speaking about indexing, not about dimensionality reduction. Maybe I just made it slightly fuzzy, but lemma gives us not only random projections as the supported, somehow mathematically supported method, but also the idea of randomly built trees. Instead of just following some algorithmically strict procedure, let's do some random stuff. And this random stuff is proposed by Eric Bernardson from Spotify at that time. Spotify, now he's working for some other company. And this became the library called Annoy. Instead of looking for median values and sorting them, let's do the following. Let's pick 2 random points from the whole data set and build a hyperplane which is orthogonal to their distance. So they have the vector of difference, and you build orthogonal hyperplane, and you split them by two parts. First, this allows you to split them in almost in most cases. This split will be not one versus all. It will be somehow dividing them into two parts. And second, that it has some theoretical support, which allows you to build the good shallow tree of logarithmically deep tree, which will be still good in searching for nearest neighbors. So if KD3 was absolutely unacceptable for highly dimensional cases with even big number of elements, Annoy, even with a single tree, can give you a pretty good starting point. Of course, there are some tweaks to make it even better. So for now, using random projections, we build shallow enough logarithmically deep tree, which allow us to search for nearest neighbors. Also, we use soft threshold, meaning that even if we search for this point and it is close to the border, we will search both sub trees. So we will definitely spend some computations to border cases. Okay, border cases previously were not considered, now they are considered. And of course, the beautifulest idea is that, yeah, so we build logarithmically deep tree, so we can only do, I don't know, 20 projections for our data for a single tree. But what about building multiple trees? What if we use many trees, 100 of trees? 100 multiplied by logarithm is still a small number. So 300 computations, 50 computations, they are still very fast. And in this case, we can achieve a very good result. So here is the example of two-dimensional case. So how it will look like. And here is an animation which shows how to utilize multiple search trees. So this is the example. All this, you can read this paper with explanation. And the beauty is, so this is what will be the result. You see, unfortunately, it gives you not very good in terms of circle. Yeah, so it's not circled nearest neighbors, but multiple different trees give you multiple different results. And in the end, you have few trees. Each of them will return you some neighborhood, which will be overlapping, but different. And your result is almost good. Okay? So with multiple trees, you obtain this region of neighbors, and it is much better than just a random portion. Yeah, the question? It's solved by first random projections, by choosing not axes and hyperplanes which are parallel to the axis, but some random which are somehow different. Multiple trees, yes, which I think can be applicable to KD trees. So if you build multiple KD trees, yeah, it can be. But KD trees never proposed us this. Annoy said that we will do this, multiple trees. And also, now we have this theoretical support. So previously, when the KD trees were invented in 1975, there were no Johnson, Linden, Strauss lemma proven. And it was proven 20 years later, allowing us to say that this is good to do random projections. Okay. What's our lecture? Yeah, we're studying this. Okay. And one of your tasks in the homework will be to use Annoy as the extra task to index the data. Yeah, the picture, which was on the paper, and what about building trees without vectors? So for now, we spoke about only a vector representation of the data. But what if we don't have vectors? Is it possible to build such a tree having only metric space, as is NSW? There are multiple such data structures, but I highlighted this one because actually the author of this method is very famous person. His name is Sergey Brin, and he later invented Google. You know, this small company in the United States, Google. Heard about it? Yeah. So when he was writing his master or PhD thesis, he was exploring this idea that the tree can be built only based on the metric. And of course, if you have a metric, you can define what is called a sphere. Yeah. So it's enough to have a metric to like fix radius and say whatever falls into this metric will become the content of the sphere. And then he said that let's build spheres. Okay. And then to build a sphere, you need only the center and the radius, so no vectors actually required. And then the procedure of splitting is based on what is called the vantage point. And the selection of vantage point is the following. It tries to do what? What is second moment, who remember? Second moment is variance. The centered second moment is variance. Beautiful. And it's doing the following. It tries to minimize the spread given this vantage point. So you take the point and you try to separate the data on those which are laying inside point plus radius and outside. And it tries to do the following. So it tries to do that the second moment, the variance inside the sphere is minimized. Okay. Of course, this is some random process. It doesn't mean that this is absolute minimum. So it's randomly samples S. So it takes some number of points from the data set and tries to use them to minimize the spread by splitting the data into internal and external. And this picture shows that first we choose the B1 sphere. B1, where's B1? B1, okay. So internals and externals. Then between B3 and so on, so some vantage points. And there's a search procedure given, there's a construction procedure given. So it's possible to build a tree without a notion of vector, only based on the metric. If you are lost in this point, summary. You remember that search trees, original search trees, which were invented 61 years ago, 1960, they were to fastly search for scalars with an order operation. So some discrete elements which are sorted by some property. This was not enough for computer graphics. Computer graphics brought us the challenge that we need to be able to store 2D, 3D objects. First was quad tree. It was splitting space into 4 parts, quadrants, and distributing the data among these quadrants. There were some optimizations to guarantee that the depth of the tree is logarithmic. Then next year came the k-dimensional tree, which said, oh, let's make dimensionality arbitrary. And here's the procedure. Not only 2 and 3, but 10 will be also okay. And then with support of mathematics, Johnson, Linden, Strauss, Lemma, a NOI data structure, again, search tree, binary search tree, no significant difference, which was actually supported by some weakening the constraints of search and adding multiple trees, allowed us to get very fast and very good results in nearest neighbor search with trees, which was not previously possible. So for KD3, multidimensional space was closed. KD3s could not work in multidimensional space. And NOI works perfectly, and it searches for recommendations in Spotify for you right now, if you listen to Spotify. And also I showed you that there are some data structures which allow us to build the tree without a vector representation. So yeah, maybe we have some problems with introducing high dimensions, but what about forgetting about high dimensions and moving to some metric space and working only in terms of spheres and variance? And here is the vantage point tree as an example. Of course, multiple other trees. This off topic is mostly to show you that trees are solving multiple different problems, not only problem of nearest neighbor search. For example, interval trees are indexing not single vectors, but the intervals, so the pairs. They are created for Olympiad programming mostly. So only those who do a lot of competitive programming know how to implement interval trees and to use them for solving problems. Actually, I never met it in my education, and I know that this is mostly for brain teaser. Yeah, they're useful when you store intervals. Like it can be a good index when the origin of data is interval, but in my practice, I never used them, so I cannot show you how to build it right now. What else? Yeah, that's the construction of interval tree, and the idea is that each interval, like each set of intervals, is split into those which are mostly to the left, or completely to the left from the separating point, completely to the right, and which are intersecting. Okay, so and then we construct the tree based on this fact. So those which are intersecting, those which are to the left and to the right. And search is, we compare to the separating node, and if our search goes to the left node, we go to the left node, to the right, and otherwise we search inside the node itself. So it's a homogeneous tree, it stores the nodes everywhere. The generalization of interval tree is BSP, binary space partitioning. The idea is to generalize an interval to a polygon. Instead of using just a scalar interval, we will use a multidimensional polygon. And the beauty of the data structure is that we use the same terms. We use intersecting, behind, and beyond. Instead of a single value, we use a hyperplane. So the plane separates our space into which is behind the plane, in front of the plane, and separating the plane. And it gives us a powerful tool. You remember we started from computer graphics, to sort elements for those which are invisible, so those which are behind some plane, which are visible, and which are on the intersection. So which are in front, for example, should be rendered fully, which are behind, they are just hidden for us, we don't see them, and which are on the intersection should be considered wisely because they are on the intersection. They should be rendered in some different way. For example, they should be computed the actual polygon which is displayed, so the part, and then displayed to you. So BSP trees as a generalization of interval tree is very useful for computer graphics. And the element here is not a single vector, but a polygon in a multi-dimensional space, usually 2- and 3-dimensional spaces, of course. Are there any trees left? Of course, tree is very popular. So the nature of a tree is to give you a chance to search for something in logarithmic time, given a big number of elements. The logarithm is like the holy grail of this. So we always want logarithmic time because faster is only the constant. And ball trees, which are also utilizing the idea of distance and spheres, M trees, R trees, R star trees, oct trees, which are generalization of quad trees. So they are like 3-dimensional quad trees with 8 rather than 4 blocks. So all these trees are used somehow useful and can be met in different indexing applications. A lot of them now not only the part of information retrieval and computer graphics, they are also the part of databases, because for now you know that databases start supporting different new data types. So if previously storing a vector in database was something strange, today a vector is just a first-class citizen in databases. So when Postgres, MS SQL, other databases, they support vectors. That's why they should support fast search for vectors. And to do this, they use R trees, M trees, KD trees, and so on. I think it's enough for today. We are here for 3 hours. Thank you very much for attention. If you have any questions, general, exact, you're free to ask. No questions. You're perfect. You're so beautiful. I love you guys. And I hope to see you on the lab. At least. No? Why? No, you don't like labs? You like labs. You don't like labs. Why?
I don't remember.
You don't remember why you don't like. You don't want.
I don't remember it today.
Okay, on the lab. So when you come. So first come and then you dislike it. It's my suggestion. Okay. Any questions from online? Are you there? Khadija?
No.
No. Wonderful. Thank you very much for being here with us. I hope that this information, a lot of information today, will at least some part of this information will remain in your brain, and you will support this with the homework and the contest tomorrow. So see you. Bye.
Thank you. Goodbye.
Bye.